and partakers, Assalamu alaikum, and a very good afternoon to one and all present over here. It is a glorious moment to extend my warm greetings on behalf of Department of Economics, Postgraduate and Research Center, Poona College of Arts, Science and Commerce. Today, as a resource person, we have Dr. Tariq Masood, sir. Dr. Tariq Masood is currently working as an assistant professor economics in the Department of West Asian and North African Studies, Aligarh Muslim University, Aligarh. He is NET and JRF qualified in economics. He has done his PhD in economics from Aligarh Muslim University. He has also worked as an assistant professor in the Department of Economics, University of Kashmir, Srinagar in the past. His research areas include applied econometrics, economic growth, and energy economics. He has published research papers in the areas of microfinance, economic growth, and West Asian studies in various national and international journals. Tariq sir, we welcome you on behalf of the Department of Economics.
Thank you, Dr. Anna, for your words. I feel really privileged to be here in this research methodology workshop. Now, I will start sharing my screen.
Yes, sir.
Is it visible now?
Yes, sir. It is visible.
Okay, now my topic, basically there are two topics. One is on time series analysis and other is on regression analysis. So these two topics are basically connected. Even in the regression analysis, we use time series data and we do time series work. So I will start from regression analysis and then gradually move towards specific issues that come in the case of time series data, that is known as time series analysis. So first I will try to cover regression analysis and then time series analysis, hopefully in the next lecture tomorrow. Now, as far as regression analysis is concerned, regression analysis is one broad approach for establishing cause and effect relationship. It is one of the most commonly used statistical method for establishing a relationship between or among variables when there is a cause and effect relationship. So in social science domain, or particularly in economics and finance area, it comes under econometric methods. So regression analysis is one econometric approach for driving estimated parameters of relationship. So first I will try to say what is econometrics and what is the subject matter of econometrics. So econometrics, basically in econometrics, we deal with the measurement of economic relationships. Not only economic relationships, sometimes there may be other problems which comes from other disciplines, but there is involvement of cause and effect relationship. So there is some cause and that is causing some variable. So cause and effect, if cause and effect relationship is involved, in social science domain, we can establish that relationship by using econometric methods. Econometrics is basically integration of economics or any other social theory. So use of economics, when we say economics, it is basically theory of economics, theory that we use at the time of modeling. Okay? The next is mathematical form of modeling, mathematical economics, or any mathematical form of modeling. So by using that, we write that relationship, cause and effect relationship, in the form of in mathematical form. So this is the next stage when we write any problem, cause and effect problem, in mathematical form. And then there is involvement of statistics in that. So by using statistical methods, what we can do, we can derive values of parameters, estimated parameters. That is problem of estimation. We all know that much of statistics, that in classical statistics, basically we can divide classical statistics into two parts. One is problem of estimation and problem of inferences. So first we can derive estimated parameters by using statistical methods, and then we can test validity or significance of coefficients by using a statistical approach. So there is involvement of statistics as well. Okay? So we can say that econometrics is basically a combination of economics, mathematics, and statistics. Okay? So the relationship of economic theories are usually, we express them in mathematical form, and then we test with the given data. So econometric methods are used to obtain the values of parameter, which are essentially the coefficient of mathematical form of economic relationship. So this is the brief idea of what econometrics is, what we do in econometrics. In econometrics, we establish cause and effect relationship. This is the basic purpose of econometric exercise. And for doing that, we use economic theory, from economics, or any other theory, or sometimes we can also use logic. If there is no existing established theory in that area for that specific problem, we can also write mathematical equation on the basis of logic. So most of the time we need some theoretical background, but even in the absence of theoretical background, we can formulate some mathematical and econometric model on the basis of past experience, past research, or simply on the basis of logic. So this is the first step when we, after identifying our problem, and problem must be cause and effect type. There is a cause and there is effect. Okay. Sometimes even we didn't realize that our problem is basically cause and effect relationship, but still that problem may be of that form. Like suppose you are simply concerned with the growth rate. So you are trying to compare growth of any particular entity like country or any other growth rate over the period of time. So our purpose is simply to look whether growth rate of the recent decade is different from the past decade or not. Now, even in this problem, there is involvement of cause and effect relationship. This problem is basically problem of cause and effect relationship. When we are concerned, suppose we are concerned with the difference in the average marks of students of different schools or different universities or different states. So you are trying to compare average marks of one school with the average marks of other school. Even in that, there is involvement of cause and effect relationship. Cause is that is school, the type of school. Okay. So, and effect is marks. So even those problems, this first problem, we can deal with simple mean difference method. You can test statistical difference of mean of various schools. So you can deal simply by using mean difference method. But with the regression framework, we can do that more efficiently. You can decode layers of the problem. If you are resorting to simple mean difference test, that will not tell us the whole story. But if you are using regression analysis for that problem, you can decode various layers of the problem. You can know the exact magnitude of the differences. You can know the proper statistical difference of the different groups. Okay, so sometimes cause and effect relationships are obvious, like we are concerned with, suppose, impact of consumption on overall income, which is known as consumption function in economics. Okay? So there we know that one variable is cause, other variable is effect, and ultimately there is a cause and effect type problem. But sometimes even we are not aware of that. The problem is basically a problem of cause and effect, and that can be analyzed, that can be deal with the, we can deal that problem with by using regression analysis. Okay, as far as approach of econometrics, methodology of econometrics is concerned, these are the steps that we deal with. Numbering is, I think, it's not correct. So first step is a statement of theory or hypothesis. So first, for our problem, first we resort to any particular theory, and by using that theory, we derive some hypothesis. Okay, like as I said, that suppose our problem is to find impact of consumption on income on consumption. Okay? So there is theory for that. There are various theories, consumption theories in economics. Okay, Keynesian theory and theory of permanent income, Friedman theory by Friedman. There are a number of theories. So you can use those theories for identifying your problem. Okay, and then by using that theory, after identifying problem, we can write exact hypothesis for that. So this is the first stage, where you identification of problem and hypothesis formation. This is the first stage. Then in the next stage, we express that problem in purely mathematical form. Okay, like suppose there is involvement of two variables, y and x. X is cause and y is effect. So simple formulation, a very simple mathematical formulation is y is equal to beta 1 plus beta 2 x. Okay, here x is known as independent variable, it is cause, and y is effect, but it is also known as, x is known as independent variable and y is known as dependent variable. Okay, x is also known as regressor. Regressors, if there is involvement of more than one x, more than one independent variable, they are known as regressors, and y is known as regressant. Okay, we can also say that x is exogenous variable and y is endogenous variable. So there are various names for these variables, but basically they are cause and effect. X is cause and y is effect. Okay, once we formulated our mathematical model, okay, so in this particular mathematical model, as I said, that this is a very simple formulation. Simple because when there is involvement of, suppose, only two variables, y and x. So we are assuming that x is causing y, but there are no other causes. There are no other independent variables. So simply y is depending upon x. This is one assumption that we have in this formulation. Now, other assumption is that the model is linear. This model is basically a linear model in mathematical sense. So we are assuming that y and x are linearly related. There is no non-linear relationship between y and x. So there are number of assumptions behind this formulation. There may be there can be other formulations as well, depending upon the problem in hand. You can formulate non-linear models. You can formulate models where more than one x variable is involved. Okay, so a lot of care is needed at the time of mathematical formulation. It depends upon the data in hand, it depends upon the theoretical background, it depends upon number of things. Okay, so once we have mathematical model, once we formulated mathematical model, we move towards econometric model. Okay, now econometric model is different from mathematical. Now this is this equation is econometric representation of mathematical model, where we have added u in the last. Y is equal to beta 1 plus beta 2x plus u. Now addition of u makes it econometric model. Now the issue is, what is u? U is basically x is a systematic determinant of y. When you are saying that y is dependent upon x and it is depending upon only x, there is no other x, okay, is still due to number of factors, there must be some portion of y that is unexplained by x. Okay, so x is causing y, it is explaining a sizable proportion of y, but still there is unexplained portion, and for that unexplained portion we are adding u in the model. Okay? Our relation are not like scientific relation where there is an exact relationship between variables. Okay, in social science domain, almost all relations are imperfect. Okay, they are not exact type. So even if there is a one broad determinant of y, which is x, and there will be some unexplained portion of y, and for that we are adding u. Now u is known as error term. In formal sense, it is known as error term. Okay, so we have to add error term in the model, and now addition of this error term, which accommodates number of things. Error term is basically unexplained portion of y, but there may be number of things that are accommodated in u. Okay, like suppose there are a number of other determinants of y, and by mistake you have not added those determinants in y. So all those determinants are by default included in error term, because you are not adding all those determinants in the formal model. So obviously they are included in u. So you also include all the excluded determinants. Suppose the original relationship is non-linear, but by mistake you are formulating a linear model. Like in this case, we are formulating a linear model. So that non-linearity is also included in u. So number of other things, number of other factors other than x are included in the error. This is the basic difference between mathematical approach and mathematical model and econometric model. Okay, so once we have formulated econometric model, next step is to obtain the data. For this simple model, you need data of y and x. With the given data, our purpose is to estimate unknown coefficients, which are beta 1 and beta 2. So once we know the values of beta 1 and beta 2, we can use them for policy purposes and for various other purposes like forecasting. So once the model is estimated by some statistical method, we can use those estimated coefficients. Here we have estimated coefficients beta 1 and beta 2. Beta 1 is minus 299 point something, and beta 2 is 0.7218. Okay, so with this estimated model, you can, after hypothesis testing, obviously we have to apply hypothesis testing before finalizing the model. Okay, so once your model passes the hypothesis testing stage, you can use this model for forecasting purpose. You can use this model for various other policy purposes. Okay, now coming to data, there are various data issues. When we go for data, there are various issues. Broadly, we can say that there are three types of data that we use for establishing cause and effect relationship. Okay, so when we establish cause and effect relationship, basically we are trying to establish a relationship between variation of x and variation of y. We are looking whether changes in y or due to changes in x or not. Okay, if there is some relation between change in x and change in y, we can say that there is relationship between y and x. Okay, so this relationship is basically about a relationship of variation. Okay, so variation in any particular variable can be observed in three ways. One is that a particular variable, if it is a time series data, time series is a set of observations on the values that a variable takes at different times. Okay, so the unit is same, the entity is same, there is variability over the period of time, like data of a particular country, GDP of India over the period of time. So when cross section is fixed, when we are seeing GDP of India, so that cross sectional unit or entity is fixed, it is India, and we are observing GDP over the period of time. So there is variability over the period of time, but unit is fixed, it is one unit. In case of cross-sectional data, okay, cross-sectional variability, there is we are recording observations at a fixed point of time. The time is fixed, but there is variability over the space. Okay, GDP of suppose South Asian countries in the year 2022. So time is fixed, but there is variability over the space. Countries are changing. There are a number of countries in South Asia, so there is variability over the space. This is cross-sectional data. And in case of panel data, we combine these two dimensions. So in panel data, there is variability over the time and there is variability over the space. Both the dimensions are involved in panel data. Okay, like GDP data of South Asian countries from 1991. So there is variability over the space. All the countries are involved, and there is variability over the period of time because we are recording data over the period of time. So this is a combination of time series and cross-sectional data. Now difference, this difference or type of data matters for a number of reasons. Okay, first, it depends upon the purpose in hand. What is your purpose? So ultimately you have to choose your data set according to your problem. If you are concerned with the time dimension, you will use time series data. If you are concerned with the spatial dimension, you will use cross-sectional data. But when it comes to econometric methodology or regression methodology, there are a number of issues which are specific with the type of data. So in case of time series data, different issues arises. In case of cross-sectional data, we deal with the different issues. Okay, panel technique is an advanced technique, and I think I will not be covering the panel regression analysis, but there is a lot of work on panel analysis during last 2-3 decades. This is advanced econometric methodology. This is the form of data, time series data. We denote it as YT if dependent, we are using it for dependent variable, it is y, subscript is t. So t may be 1990, 91, 2000 to 2012. And cross-sectional data, for cross-sectional data, we use I subscript I, yi, and I is equal to 1, 2, 3, 4. And in panel data, it is YIT. I and T are defined as above. T is time and I is cross-sectional units. Okay. Okay. After type of data, now next thing that need some clarification is types of variables. Okay. There are 4 types of variables that we use in any regression analysis. Okay, first, most commonly used variable is or ratio scale variable. Okay, or purely quantitative variables in layman terms. Is those variables which are purely quantitative. But exactly for exact definition, you can say any variable is a ratio scale variable if suppose we have 2 values of that variable x1 and x2 at 2 different time or at 2 different spaces. Okay, it is a ratio scale variable if the ratio x1 divided by x2 and distance between these 2 points x2 minus x1 are meaningful quantities. Okay, so ratio is meaningful and distance between 2 points is meaningful. Okay, and further, if there is natural ordering of values along the scale, okay, we can say that the value, the variable is the ratio scale. So for any quantitative data like GDP, inflation, or any quantitative data, all those variables satisfy these criteria. X1 by x2 is meaningful, distance is meaningful, and there is a natural ordering in the data. Okay. Now next is interval scale variable. An interval scale variable satisfies last 2 properties of the ratio scale variable, but not the first. Which one is first? X1 by x2. So in case of interval scale variable, the ratio is not meaningful. Can you give me any example of interval scale variable? Anyone? Where distance is defined, there is ordering in the data, but a ratio is not a meaningful quantity. Do you have any example for that? Okay, for my information, is there anyone who is from economics background and also opted for econometrics as an optional paper?
Participants, please respond. Is there anyone from economics background?
Okay, fine. Now I will give an example for that interval scale variable. We also use time as a variable. Okay, time like 1990, 1991, 1992. Okay, so this is time is also we also use time as a variable. Now when time is variable, suppose our variable is time. Okay, so for time, ratio is meaningless. When you write 1990 divided by 1991, you get a meaningless value. There is no meaning of that. Okay, but for that variable, distance is defined. Distance between 1990 and 1991 is 1, and that is meaningful value. Okay, and also there is a natural ordering. 1991 comes after 1990. Okay, 1992 after 1991. So there is ordering in the data. There is meaning of distance between 2 values, but the ratio is not meaningful. So we can say that time is a variable which is interval scale variable. Okay. Now next type is ordinal scale variable. a variable belongs to this category if it satisfies the third property of ratio scale, that is natural ordering, but not first two. It only satisfies the last category. First two satisfy nahi hoti. Okay? Again, can you suggest me any example of ordinal scale? We all encounter such variables, such categorization. It is a type of qualitative data basically. So like grading system or division, first division, second division, and third division. So there is a ordering. Okay, first, second, third, or third, then second, and then first. Okay, there is ordering, but there is no meaning of ratio and distance in that case. Okay, when we write classes, okay, upper class, middle class, lower class. Okay, so there is ranking, there is ordering in the data, but ratio and distance are not defined in that. This is example of, these are the examples of ordinal scale. Last one is nominal scale, and nominal scale variables are they are purely qualitative variables. Okay, and for nominal scale variables, they does not satisfy any of the properties of ratio scale variables. Okay, so there is no meaning of ratio, no meaning of distance. Also, there is no ordering. Okay, an example is gender, male and female. Okay, or there may be more than two categories in case of gender, but there is no meaning of ratio, distance, or also there is no ordering in that. In case of gender, there is no ordering. Okay, so there are a number of other examples as well where there is no ordering. Caste. So in case of caste, there is no ordering. Okay, now next is basic data handling. Basic data handling means that it comes before we go to formal analysis. Okay, before going into formal analysis, formal regression analysis, you must do some basic data handling exercise. Okay, first is very important. It is looking at the raw data. You have raw data, you must look at the raw data very carefully, because most of the time we use data from secondary sources. Until and unless you are doing your own primary survey, okay, you are using data from some secondary sources. It is already feeded in Excel format or whatever. So you must look at the raw data very carefully. Okay, there may be some missing values, there may be some extreme values, okay, and that may be due to human error. Sometimes there may be errors in data feeding, okay, data in. So you must look at the raw data, and then next is graphical analysis. You must do a lot of graphical analysis before doing any regression analysis. Okay, so we can use time series plot, we can use histogram, we can use bar diagram. Okay, a lot of graphic options are there that can easily be done with the statistical software, and you must do that. Summary statistics means driving basic summary statistical values like mean, variance, mode, everything. So all basic you must look at all the basic summary statistic values. Okay. In case of time series data, we can look at the components of time series. There are different components of any particular time series. There may be trend, there may be cyclical component, there may be irregular component. So all these things are part of basic statistical analysis. In any basic statistic textbook, you will find all those things. How to remove trend from the data, how to differentiate between trend, irregular component, and cyclical component. So The next is indices and base dates. Particularly in case of economic data, sometimes there may be change in base. Okay, the value may have any particular index. So you must look at those. Data transformation, basic data transformation. We have to do some basic data transformation before formal analysis, like logarithmic transformation or any other transformation. So we have to do that before going to formal analysis. Okay. Okay, now next slide is of regression analysis. What is regression analysis? Introduction of regression analysis, basically. Now this term is confusing because regress means it is something different. The literal meaning of regression is different. So why we call it regression analysis? It is simply due to experiment that was conducted by Francis Galton. Francis Galton was concerned with the average height of children and parents. Okay, so he was trying to establish a relationship between height of parents and height of children. He was looking whether there is some relationship between that or not. Okay? So what he found that ultimately, when we look at the large parents with large height, in number of cases, their children also have large height, but on an average, there is a tendency to regress towards the average value. Okay, so when we look at number of short height parents, okay, the average height of all these children is moving towards the average, and same is true for the large height parents. Okay, so this is the term regression. The word regression, we use it simply for that reason, because in that particular experiment there was a regression towards the mean. So Galton called it regression analysis. Okay. Regression analysis, as I said earlier, is concerned with the study of dependence of one variable, the dependent variable, on one or more independent explanatory variables with a particular purpose of estimating or predicting the mean or average value of former in terms of known or fixed values of the later. Okay. Now this was the experiment that was done by the Francis Galton. Okay, this x axis is height of fathers, okay, in inches, and y is height of sons in inches. Okay, so when we move towards x-axis, ultimately there is a move of height of sons, but there is a regression towards mean. Okay, so this was the first experiment due to which this term came into effect. Okay, the primary purpose in exact form is to estimate population regression function. This first equation is population regression function. Yi is equal to beta 1 plus beta 2 xi plus ui. This is known as population regression function. So our purpose is to estimate this function, to estimate beta 1 and beta 2, which are unknown quantities, unknown values, which belongs to some population. Okay, on the basis of sample regression function. Yi is equal to beta 1 cap. Here we are adding cap on beta 1. These are estimated values which we are estimating with the given sample. Okay, now this whole exercise is almost same in the statistics. Statistics as a discipline is basically about this, that there is an unknown parameter which belongs to the population, and we have a particular sample. We cannot cover the whole population. Our purpose in statistical analysis is always to find is to estimate parameter on the basis of given restricted sample. Okay, so only thing that we have is is a particular sample, and we are concerned with the population. So we calculate, we estimate parameter on the basis of sample, and then we generalize that parameter for the population. Now tell me why we cannot cover the whole population, why we deal with the sample. बहुत ही simple question है, that why we deal with the sample, not with the population. Now I need some response, at least some response. Why it is difficult to cover the whole population? Why we cannot conduct census? Okay, there are some responses in the chat box. Sorry, I was not looking at the chat box. Okay. Okay, so there are some responses like studying population is costly, or it is impossible to cover population as people keep moving or migrating. It is not easy to keep track of all population, as not all stay at one place at same time. All these answers are correct to some degree, okay, but when we use this word population in statistics, it is different from general use of this word population. Okay, when we say population in a statistical sense, okay, it means all the entities, it may be humans, there may be banks, there may be countries, all the things. Okay, so the issue is that when we suppose we are concerned with the human population, okay, so in a statistical sense, the population means all the people, all the past peoples, all the current people, and all the future people. So when we include everyone, then we can say it is a population. So in a sense, in a statistical sense, we can never cover the whole population. Even if you are conducting census of all the current people, living people, okay, it is not a population in a statistical sense. So in a statistical sense, population is always a hypothetical idea. It is not a real idea. We cannot cover population because all the peoples are not there. कुछ पहले के लोग हैं जो अब नहीं है दुनिया. There may be some current future population, so we cannot cover whole population. So it is not a feasible thing. In case of time series data, suppose we are concerned with the GDP values starting from 1991 up to 2020. So you have all the values. All the values are available. GDP of 1990, 1991 up to 2020. All the values are available. Sometimes we confuse those values with the population, that we have all the values. We are concerned with the GDP of last 3 decades and we have all the values. But in case of time series data, the concept of population, which is known as stochastic process, is different. It includes all the unrealized values. So GDP value of any particular year, suppose 1991, is one particular realized value, realized due to number of things. Okay, there are number of unrealized values. Okay, so we include all the unrealized, infinite unrealized values of GDP in that definition. So again, even in the time series data, population is a hypothetical idea. We cannot cover population. Even if we have budget, even if we have time, even if we have human resources, we cannot cover whole population, because in a statistical sense, the population is a hypothetical idea. Okay, and most of the time, or all time we have samples. Sometimes sample may be small, sometimes sample may be large, like sometimes we conduct primary survey where sample size is suppose 2000, 5000. You have nationally representative samples from NSSO where the sample size is household level sample size is around 1 lakh. Okay, and individual population covered in all those samples is around 5 to 6 lakh. Okay, you have National Family Health Survey where the size of sample is quite large. So the size of sample may vary, but everything is sample. Even the census data in statistical sense is a sample. Census is a complete coverage of population. Okay, but in statistical sense, that population census is also a sample. It is not a population in the statistical sense. Okay, it is a sample because it covers only the living population. Clear? Or still there are some confusion, because you have to clarify all these concepts, not only for regression analysis, for any statistical analysis. You must know what is population in statistic. Okay, so I think candidates are facing some issues specific to unmuting themselves. They can't unmute. So
I have allowed them. Actually, initially, now I have allowed them to unmute themselves.
You can allow at the time of question. Yeah, so when there is
it will keep troubling.
Okay, now this is graphical representation of sample and population regression line. Okay, this line is a population, PRF is a population regression function, population regression line where y is dependent, beta 1 and beta 2 are true unknown coefficients, and x is independent variable. Okay, but as I said that we cannot know the true values of beta 1 and beta 2. We have to deal with a particular sample, and ultimately we have to derive estimated values of beta 1 and beta 2. So this is sample regression line. Now, corresponding to any particular xi value, there is a true y value. Okay, now the population regression function representation is expected value of y conditional upon x. Okay, average value of y. This expectation is simply, the simple meaning is it is the average value of y conditional upon x value. Okay, and this point on the corresponding point on sample regression function is yi cap. It is the estimated value of y, not true value. It is estimated value of y on the basis of sample. Now this difference between true y and y cap is ui cap. It is error term that we are drawing from sample regression function on the basis of sample. So this is known as, there is a different name for that. It is known as residual term. Okay, and this difference between y and the true average of y, expectation of y conditional upon x, this whole difference is ui. This is error term. Okay, so this is pure error term. Even if we have population, somehow there will be difference between the true y and average y. Suppose you are estimating the population regression, you have complete coverage, you have all the data, and you are estimating the whole population. Okay, you are estimating beta 1 and beta 2 on the basis of whole population. There will still be an error term. Why? Because there may be some unexplained portion of y, unexplained, that is not explained by x. There may be some other reasons like non-linearity, exclusion of variables, randomness in human, number of things. So still there is an error term. But when we are dealing with the sample regression function, sample data, you have a difference that is known as residual UI cap or UI hat. Okay. Now, first step, as I said in the introductory slide, that there are two stages in any statistical exercise. One stage is estimation, and next stage is hypothesis testing or statistical inferences. Okay. So first we will cover this estimation part. Now our purpose is well defined in the above slide, that there is a true population regression function and we have sample data. So we have to estimate that true population regression function on the basis of sample data, and that function is known as sample regression function, where we get estimated values of beta 1 and beta 2, beta 1 cap and beta 2 cap. Okay, so we get estimated value. Now the question is, what is the method of estimation? How we derive beta 1 and beta 2, which are as close to beta 1 and beta 2 as possible. Okay. In other words, how should the sample regression function be constructed so that beta 1 cap and beta 2 caps are as close as possible to beta 2, even though we never know the true beta 1 and beta 2 values. Now this is the next problem, that in reality we never know the true values. Still we are trying to move towards the true values. Okay. Now from any given sample regression function, this is sample regression function, this part beta 1 cap plus beta 2 cap xi, we can write it as yi cap. So yi, the true value, is equal to yi cap estimated value plus ui cap, which is residual, estimated error term or residual term. Okay. From this equation, after rearranging, you can take ui to left side, ui cap is equal to yi minus yi cap, or after putting yi cap values in beta 1 beta 2 form, it is yi minus beta 1 cap minus beta 2 cap. Now I am avoiding all these mathematical derivations, but still some mathematical derivation is needed. Okay, some mathematical representation is needed. I am trying to avoid these things as possible as I can. Okay, so ui cap is basically equal to yi minus beta 1 cap minus beta 2 cap. Now our purpose is to minimize this residual term as possible as we can do. Okay, so we have to minimize this ui cap. Yeah, this is the graphical representation of the same phenomenon. We have some sample regression function, and there are a number of data points corresponding to x and y. Okay, and there is a deviation of all those points from the sample regression function. So that deviation is a residual term. Okay? U1, U2, U3, U1 cap, U2 cap, U3 cap, and so on. Okay, so all these deviations are basically deviations from sample regression function. So we have to fit a line that is close to all these points. Okay, good fitted line. Okay, so for that we need some method. Okay, now that method is OLS method of ordinary least square. We call it OLS. Okay. Now in OLS, what we do, we try to minimize this residual term, but we, in a very specific sense, we minimize ui cap squares, sum of squared residuals, not residuals, but sum of squared residuals. So when we take a square of both sides, ui cap square is equal to yi minus yi cap square, and then we take summation, because we have to minimize sum of residuals, u1 plus u2 plus u3 and so on. So we have to minimize this whole sum as possible as we can do. Okay. Now for those candidates, for those participants who are aware with the calculus differentiation, they know that there is a method in calculus for getting maximum and minimum values, for driving maxima and minima. Okay, what is that method? How we do that? How we get maxima and minima? Okay, the method is to differentiate. Suppose we are maximizing any function, we have to differentiate that function with respect to independent variable. Okay, and then first order, there are two conditions: first order condition and second order condition. First order condition is same for maxima and minima. It is same for optimization. dy by dx is equal to 0. So we have to equate first derivative to 0, and then we can drive the condition. Okay, and second order condition for ascertaining whether the point is maxima or minima, and which is second order condition, second derivation. So if the value of second order derivative is negative, we say that there is a maxima. If it is positive, then we say that there is a minimum. So by using that logic, we can differentiate this summation of ui cap square with respect to beta 1 and beta 2. You have to differentiate this function with respect to beta 1 and beta 2. After differentiation, and once you equate those partial derivatives to 0, you get two equations, because we are taking two partial derivatives, one with respect to beta 1 and then one with respect to beta 2, and we are equating two partial derivatives with respect to 0. So we are getting two equations, and these equations are known as normal equations. First normal equation is summation y is equal to n beta 1 cap plus beta 2 summation xi, and then next is summation yi xi is equal to beta 1 cap summation xi plus beta 2 cap summation xi square. Okay, after solving these are two equations. You have to solve these two equations for the value, two equations and two unknown. You know the rule. For solution, number of equations must be equal to number of unknown quantities. So we have two unknown values, beta 1, beta 2. We have two equations. Now, summation values, we are getting these summation values by data. You have data of yi, you have data of xi. With the given data, you can generate new column yi xi, multiplication of yi xi, you can generate xi square. Okay, so after you have yi xi and xi square, you can take summation of all those columns. Okay, so these values are basically known values. Now in first equation, there is involvement of small n. Now this small n is size of the sample. So size of the sample is also known. You have sample size of suppose 20 observations, 100 observations, 5,000 observations. So you have to put that. Okay, you know the values of all the summations, you know the value of n. So this is basically two equations, two simultaneous two equations which can be solved for two unknown quantities. In mathematical formulation, for the formula, you can use beta 2 cap is equal to summation xi yi divided by summation xi square. Now this x is small x. In the normal equations, we are using capital Y, capital X. Now this is a small x. Small x is basically deviation from the mean. So small x is equal to capital Xi. Small xi is equal to capital Xi minus x bar. Okay. So once we take this deviation from the average value x minus x bar, that value is small x. Okay. So for getting beta 2 cap by this formula, what you can do, you can generate some new columns, a small xi, a small yi, and a small xi square. Then you can put all those values here. Okay. After generating xi by I column, you can put all these values and you will get value of beta 2. Okay, and in a similar way you can get value of beta 1. So this is the method of OLS. OLS tries to minimize sum of squared residuals, not residuals. Why we minimize sum of squared residuals? There are reasons for that. Okay, because there may be some extreme observations in the data or some outliers. So if there are outliers, when we take square large values, square of large values is even more larger. When we take square of 2 is 4, square of 6 is 36. So as we move towards large values, square of large values is even more large. Okay, so for that reason we use square term, because we give more weight to the large values, and ultimate purpose is to minimize the deviation. So if there are large values, there is a large deviation, and we are trying to minimize that. Okay, in a sense they must get less weight in this method. Okay, so this is the idea. This is the method by which we derive our beta coefficients on the basis of sample data. We have sample data, we can generate beta 1 and beta 2 values by using this method. Okay? Now next question is why OLS? There are a number of other methods as well. There are a number of other methods for estimation, like maximum likelihood method, or number of methods. Okay? So why we use OLS method? We use OLS method because OLS estimators have some wonderful properties. Okay, the statistically desired properties. First is they are unbiased. What is the meaning of unbiased? Now I cannot see even the chat box here, that there is some issue in. Okay, now chat box is visible. So what is the property of unbiasedness? All these things are part of basic statistics. When an estimate is known as unbiased estimate. Okay, there are some responses. Okay, there are some responses, but I think they are not satisfactory in a sense. Now, property of unbiasedness, or for all these properties, you must know the idea of sampling distribution and repeated sampling. Okay. Now the idea is that we are getting our estimate by using one sample. Now suppose we have access to number of samples from the population. So first you are using one sample, you are driving your estimate by using first sample, then you are using second sample from the same population, and you are again estimating parameter, and from the third sample you are again estimating the parameter. The problem is you will get different estimates from different samples. Okay. The property of unbiasedness is that suppose we are conducting this experiment large number of times, and we are getting number of beta 2 values, beta 2 from first sample, beta 2 from second sample, beta 2 from third sample, beta 2 from nth sample. When we take average of all these betas that we are getting from number of samples, average of all these betas is equal to true population parameter. Okay, so if any particular estimator satisfies that property, that estimator is unbiased estimator. Okay, so OLS satisfies that. If you have access to lot of samples, you are getting lot of estimates. Ultimately, the average value expectation of beta 2 cap is equal to beta 2. Okay, the average value of sample estimates is equal to true population parameter. So this is the property of unbiasedness. Now, next property. Next property is property of minimum variance, that these betas, okay, the variability of betas is minimum. That it is true that we are getting different estimates from different samples, okay, but variation is minimum. If you are using some method where you are getting number of estimates from different samples and there is a lot of variability in all those betas, we cannot say that they are true representation of population. So there is a minimum variation possible. Okay? Combined with the first property, when we say that any estimator is unbiased and it has minimum variance, those estimators are known as efficient estimators. Okay? So any estimator is efficient if it satisfies first two properties. OLS estimates are also consistent. That consistency means that as the sample size increases indefinitely, as we are moving towards population, as we are increasing sample size, the value of estimator beta to cap is converging toward the true population value. So as we are increasing sample, the value of estimator is converging toward the true population parameter. This is the property of consistency, and OLS satisfies that property also. Estimated coefficients are normally distributed. I think you know what is normal distribution. ये basic statistics में ये सारा कुछ होता है. You can revise that. So they are also normally distributed. They have minimum variance in the entire class of unbiased estimators. So these are the 5 properties that are satisfied by the OLS estimator, and this is one solid reason why we use OLS in a number of applications. There are cases where we cannot apply OLS, non-linear formulation of models. We have to move towards some other methods, but if OLS is applicable given the nature of the problem, OLS is a better option. It is quite easy to understand, okay, because there is a very simple mechanism where we minimize sum of squared residual, and the whole mechanism is basically, it comes from the differentiation, okay, first and second order, and you can understand the whole process. Other methods they are tedious, it is difficult to understand them, okay, so we must use OLS where the problem allows us. Okay, this is the distribution of graphical distribution of estimated parameter by OLS method. Okay, they are distributed in a very there is a normal distribution of all these graphs. First graph is of beta 1, and this is standardized beta. Standardization means that we are taking beta 1 minus beta 1 cap minus beta 1 divided by standard deviation of beta 1 cap. This is a standardized value. Even in case of mean difference testing, we do all these things. Okay? So the original beta 1 cap itself is a normally distributed, and expectation of beta 1 cap is equal to beta 1. That means when we take average of all the betas, it is equal to true population parameter. Okay, now next is assumptions of regression model. When we do regression analysis, we make a lot of assumptions. There are a lot of assumptions behind regression analysis. First is regression model is linear in parameters, though it may or may not be linear in variables. So the model is linear in parameter. We cannot allow non-linearity in parameters for the simple regression analysis. Okay, X values are fixed or X values are independent of the error term. Okay. The meaning is that there is no correlation between X and U. When you are writing your regression function, Y is a function of X, and in the last you are adding UI. Okay, so UI is something different other than X. UI accommodates other factors other than X. So there should not be any correlation between x and u if there is correlation. That means x itself is an endogenous variable because ui is a part of y and there is correlation between x and u. So indirectly there is a correlation between x and y. So x itself is an endogenous variable and we cannot write a single equation. There is a need to write two equation model where in the first equation y is a dependent variable and in the second equation x is a dependent variable. So it comes in the domain of simultaneous equation modeling that we have in econometrics. But for the normal regression analysis, one line regression analysis, we assume that x values are independent of the error term. Okay? Now the mean value of disturbance term ui is 0. That there are some positive residuals, positive disturbance term, there are some negative disturbance term around population regression function, but on an average, the value is 0. So some are above the line, some are below the line, but when we take average, that average is 0. Okay. Homoscedasticity or constant variance of ui. Now this is next assumption that is needed for the ui. The assumption is that variance of the error term or disturbance term is same regardless of the values of x. So when we move towards x-axis, x values, the variability of error term is same. There is no significant change in the variability of error term. This is the assumption of homoscedasticity. Next is no autocorrelation between disturbances, no autocorrelation between error terms. This problem arises mostly in the case of time series data because one difference between time series data and cross-sectional data is natural ordering. In case of time series data, there is a well-defined ordering in the data. As I said that 1991 comes after 1990. But in case of cross-sectional data, there is no such ordering. You are allowed to disturb the ordering of the data. You can put, suppose you are dealing with the South Asian countries, you can put Pakistan at the first place, or you can put Pakistan in the last place. It will not affect your estimate, your analysis. But in case of time series data, you cannot disturb the ordering of the data. There is a natural, well-defined ordering, and we have to deal with that. So when there is a well-defined ordering, there is a chance that there is autocorrelation. You know what is correlation? Correlation means relationship between or amongst different variables. Okay, autocorrelation means correlation in the values of a particular variable. Okay, between two or more values of any one particular variable. So here the assumption is that there is no autocorrelation in the values of error term. Okay, so when we are dealing with the time series data, because there is autocorrelation in the values of y, there may be autocorrelation in the values of ui. Okay, so this arises mostly in the time series context. In case of cross-sectional data, because we can disturb the order, we can change the setting of the data. It is not a serious issue. And next is the number of observations. Total sample size n must be greater than the number of parameters to be estimated. So if you have a simple regression function where you have y and x, you have two parameters, beta 1 and beta 2. Sample size must be greater than 2. If sample size is 2 or less than 2, we cannot estimate parameter. Okay. Next, there are things that we assume for x variable. The x values in a given sample must not all be same. If all the x values are same, we cannot establish relation between x and y, because as I said that cause and effect relation is basically we are establishing relation between variation of variables. So when there is no variation, there is no relation. When the all x values are same, obviously there is no variation in x, there is no relation between y and x. So there must be some variation. This is needed. Technically, variance of x must be a positive number. Until and unless variance of x is positive, there is no relation. Further, there can be no outliers in the values of x variable, that is values that are very large in relation to rest of the observation. There should not be extreme observation. Okay, now suppose all the values are, suppose the mean value is 25. That means there are some observations which are less than 25, some are more than 25, but on an average, the value is 25. But suppose you have one observation which is 2500. So that observation is an extreme observation, and if you are adding that observation, it have extreme repercussions for the overall analysis, if extreme repercussions for the estimated values. Okay, so there should not be extreme values. In the case of multiple regression model, when we multiple regression means we have more than one x. Okay, so there are at least 2x or more than 2x. So in that case, in case of multiple regression model, there should not be exact relationship between two or more independent variables. Okay, now technically when you add two variables, two independent variables, x1 and x2, okay, on the basis of theory, we know that there is an effect of income on consumption, but there is also effect of wealth on consumption. So in the whole consumption theory framework, there are at least two variables which are different, and they have their impact on consumption, income and wealth. Now we have to add income and wealth because these are two different determinants. If you are excluding wealth, that effect will go into UI term, and that will make UI a systematic component. UI is basically a random component. It must be unsystematic. There should not be any correlation in the successive values. The mean value of UI must be equal to 0. But if you are excluding any significant determinant like wealth, obviously there will be that effect will go into UI, and UI will start behaving like a systematic variable. Okay, so we are bound to include wealth. But when we include wealth, the problem is there may be high correlation in reality when we take data of income and wealth. So you will observe that those people who have large wealth are the same who have high income. So there is overlap between these two variables, and there is high correlation between income and wealth. Okay, so on the in the theory, these are separate variables. Income is something different from wealth. They are their definition is different. They are different. But when we deal with the data, ultimately there is a correlation between income and wealth. So this problem is basically a problem of data. Okay, it's not a problem of theory. This is not a problem of formulation. This problem is a sample specific problem, and it arises due to availability of data. Data is such that two variables are related. Okay, so we must do something to avoid multi-collinearity if there is exact relation, or if there is a high correlation. Okay, we have to apply some solution for that. Now next is there is no specification bias. A specification bias means that you are writing a true function. Okay, you are not excluding any important variable, you are not adding any irrelevant variable, you are not wrongly writing a linear formulation where non-linearity is needed. Okay, so in all those respects, your specification, mathematical specification and econometric specification are correct specification. If you are making any mistake, that will be problematic for the model. Now for inference purpose, if your purpose is simply estimation, you need all these assumptions, but if you are concerned with the hypothesis testing, which is almost always needed. So we need one more assumption that UI must follow normal distribution. Residual term must follow normal distribution. Normality is needed for application of T test, Z test, F test. Okay. Now, apart from purely linear representations, okay, purely linear representation, which is y is equal to beta 1 plus beta 2 x. There are some other representations that we use in empirical analysis. Okay, so first I would like to clarify the meaning of beta 1 and beta 2 in simple linear framework. In case of linear model, can you tell me what is beta 2? When we write a simple linear model, y is equal to beta 1 plus beta 2 x, what is the meaning of beta 2? What exactly is beta 2? And what is beta 1? Okay, anyone? This is a very simple mathematical model that we deal in the class 7, 8. Simple linear equation. Beta 2 is slope and beta 1 is intercept. That's true. This is purely mathematical nomenclature for beta 1 and beta 2. Now, when we, if you are aware with the calculus, so the meaning is when we differentiate this function with respect to x, first linear function, dy by dx, you will get beta 2. dy by dx is equal to beta 2. So what is dy by dx? What is the meaning of dy by dx? I think you all are aware with the simple calculus. We all know simple calculus. So what is dy by dx? What is meaning of that? Because beta 2 is basically dy by dx. It's true. You know, there is a response by Sayre. Change in y due to change in x. Dy by dx is change in y due to change in x. Now, basically, it is change in y due to 1 unit change in x. Dy by dx is change in y due to 1 unit change in x. Okay, so once there is 1 unit change in x, y changes by beta 2 unit. Okay, now when we suppose we are not using marginal effect of x on y, Sanjay Saha. Okay, it's true, marginal effect of x on y. Okay, so once there is a change in x by 1 unit, there is change in y by beta 2 unit. Okay. Now, next formulation is log linear. We call it log linear formula or double log model. We are taking log transformation of y and we are taking log transformation of x. Okay, so both the variables, dependent and independent, we are transforming them in logarithmic form. Now the question is, why log transformation? What is the need of transformation? We do a lot of log transformation in econometrics. Why we do that? What is the need of logarithmic transformation? What are the benefits? Okay, there are a number of reasons for logarithmic transformation. The first reason is that log stabilizes the variance of the data. So if there is a lot of variation in the data, when you take log of that data, there is a stabilization of variance. Okay, we also take log for making any non-linear model, for converting any non-linear model into linear form. Like one example, which is very common in economics, is Cobb-Douglas production function. So in Cobb-Douglas production function, y is equal to beta 0 plus labor to the power beta 1 and then capital to the power beta 2. Now this function is a nonlinear function. Y is equal to beta 1 L to the power beta 2 and k to the power beta 3, suppose. Okay, so because there is a involvement of beta 1 in that form, it is a non-linear function. But once we take log of that, we can convert that non-linear mathematical model into linear model. Okay, so this is one use of taking log. Okay, now the question is, what is the meaning of beta 2 in this model? In the case of double log model, what is the meaning of beta 2? In the case of first model, linear model, beta 2 is marginal effect. It is change in y due to 1 unit change in x. But what is the meaning of beta 2 in second model? In case of second model, it is basically percentage variation. We define it in terms of percentage variation. So beta 2 is when there is 1% change in log of 1% change in x, there is beta 2% change in y. This is the interpretation. When there is 1% change in x, there is beta 2% change in y. Okay. Now third model is log linear model, where we are taking log of y but not log of x. We are using x in a raw form, but we are transforming y in logarithmic form. So log of y is equal to beta 1 plus beta 2 x. Now in this case, interpretation is when there is 1 unit change in x. We are using unit because there is no logarithmic transformation of x. So when there is 1 unit change in x, there is beta 2% change in y. Now for y, we are using percentage because y is in logarithmic form. So when there is 1 unit change in x, there is beta 2% change in y. Now the next model is linear log model. Okay, in case of linear log model, y is in raw form and log is in x is in logarithmic form. In this case, interpretation of beta 2 is when there is 1% change in x, there is beta 2 unit change in y. Now I think it is clear. Okay, when there is a log, we use the word percentage. When there is no log, we use unit change. Okay, now I will leave other models. I think mostly we do logarithmic transformation. Now I will come to now I will move towards multiple regression model. Okay, so suppose you have more than one x variable. So in this case, we have 2 x variables, x2 and x3. So it is basically generalization of same function, population regression function in 3 variable framework, where 2 independent variables are involved. yi is equal to beta 1 plus beta 2 xi plus beta 3 x3 plus ui. Okay, so how much time is there? Can anyone tell?
Almost half an hour is left.
Okay, I still have a lot of things to cover. So okay, so in this function, beta 2 and beta 3 are basically their partial slope coefficient. Interpretation is same as in case of simple model. Here there is little difference. Partial means beta 2 is change in y for 1 unit change in x, keeping x3 constant. Now this is very important. You have to add this, keeping x3 constant. This is the meaning of partial coefficient, that when we are keeping x3 constant, we are changing x2 by 1 unit, there is change in yi by beta 2 unit. Okay, so same for beta 3. Beta 3 is change in y due to change in x3, keeping x2 constant. Now next thing that we use for after estimation, once you have the estimated values, next we go for judging the goodness of fit of the model, whether our estimated model is good or not. Okay, so for that we use two things. One is goodness of fit of the model, which is known as R square and capital R square, and then we move towards formal hypothesis testing. Okay, so for goodness of fit, we use concept of coefficient of determination R square. In case of two variable framework, it is a small R square. In case of multiple regression framework, it is known as capital R square. The meaning is same. Okay, now the meaning of small r square and capital R square is that they are basically it is a ratio of explained sum of square divided by total sum of square. Now the question is, what is explained sum of square and what is total sum of square? Total sum of square is quite obvious. It is total variation in the data, in the y values, in the dependent values. Okay, so total variability in the y values is known as total sum of square. Now the percentage, the portion that is being explained by the sample regression function is known as explained sum of square, because as I said earlier, that sample will not explain the whole part. There will be some unexplained part, and that goes to residual. Okay, so the explained part, explained due to sample regression function, is explained sum of square, ESS, and total sum of square is total sum of square, TSS. So R square is basically ratio of ESS divided by TSS. So if your sample regression function has a better fit, if it is explaining most of the y variation, then the value of ESS will be closer to TSS. Okay, and ultimately if it is exactly same, if your x values are explaining 100% variation of y data, ESS is equal to TSS, and ultimately R square is equal to 1. Okay, when x is not explaining any portion of y variation, then ESS is completely different from TSS, and basically ESS is equal to 0, and R square is also equal to 0. So minimum variance is minimum value of R square is 0, and maximum value of R square is 1. Okay, when R square does not explain any, when x does not explain any part of y, it is 0. If x explains everything of y, all the variations of y, it is equal to 1. So R square lies between 0 and 1. Okay, the value of R square, if value of R square is 1, it means there is a perfect fit. Now same is true for capital R square. In case of capital R square, we are dealing with the multiple regression framework. There is an involvement of more than one x. So ESS is basically portion of y explained jointly by all the x's. This is the difference. There is difference between ESS of simple model and ESS of multiple model. In case of multiple model, explained sum of square is percentage variation of y explained jointly by all the x's. Okay, and then the definition is same. R square is again equal to ESS upon TSS. The value again lies between 0 and 1. Okay, now next is there is a concept of adjusted R square. In number of research papers or in software output, you will find the value of adjusted R square. Now what is adjusted R square? There is one problem with using R square as a measure of goodness of fit. The problem is once we start adding additional regressors, suppose you have a very simple regression framework where y is dependent upon only one x, then next you are adding one additional x. The problem with R square is that once we add additional variable, it always increases. R square always increases when we add additional regressor, additional independent variable, even if that variable is an irrelevant variable. Even if you are adding any irrelevant variable in the model, R square always increases. So this is problematic. There must be some penalty for adding additional regression. Okay, when the value of R square always increases with the addition of regressor, is this problematic, because the regressor may be irrelevant. So for that, we can use different R square, adjusted R square. There is some adjustment for addition of additional variable in that. And last point is comparing two R square values, because on the basis of R square value, we choose models. We estimate number of models by adding X, by deleting X, and then we compare models on the basis of R square, and then ultimately we decide that this particular model has a very high R square, so this is a good model. But there is one problem. We can compare R square only when the dependent variables are same. If the dependent variables in two models are same, you can compare R square. But if dependent variables are different, suppose in the one model you have dependent variable in logarithmic form, log of y, and in the other model you have a dependent variable in raw form, y. So in these two variables are different. Log of y is different from y, and you cannot use R square for judging goodness of it. Okay, so you must keep that in mind. Okay, now next is statistical inference. Now after doing estimation by OLS, okay, then by looking at the goodness of it, capital R square. Now next we go to statistical inferences, formal hypothesis. Okay. Now the question is what is the need of hypothesis? Why we do hypothesis? Not in regression analysis, but in general, why we do hypothesis testing. Okay, to verify, there is one response to verify validity. Okay, so ultimately, as I said that because we are dealing with the sample, we are concerned with the population, but we are dealing with the sample. So somehow we have to apply some test whether this estimated value estimated from sample is a true representation or not. We need some testing, okay? Because there may be very large difference between parameter and estimated value. So there is need of some testing. In regression analysis, our purpose is not only to estimate sample regression function, but to use it to draw inferences about the population regression function. So we need hypothesis testing. The problem of statistical hypothesis testing may be stated simply as follows: is a given observation or finding compatible with some stated hypothesis or not. This is simple representation of problem. Okay. Now, when we go for hypothesis testing, we all write hypothesis for our research work, for our PhD. Okay. So when we write hypothesis, there are basically two hypotheses. One is null hypothesis, other is alternate hypothesis. Null hypothesis is basically negation of something. There is no relation between variables. Okay. There is no causation. So null hypothesis is basically negation. We in a very early stage we write that there is no negation, there is no relationship. Okay. And then we try, in the whole research process, we try to refute that, we try to reject that. And if after all the attempts you cannot reject that null hypothesis, we may accept that the hypothesis is true. Okay, so this is the process by which we do statistical analysis. So same is true for the regression analysis. You must know some basic concept: what is standard error, what is degree of freedom, what is level of significance. All these things are needed for hypothesis testing. Okay, level of significance is type 1 error. It is probability of committing type 1 error. Okay, what is type 1 error? When we can make error in two ways. One is that your hypothesis is true and you are rejecting. Next error is when your hypothesis is false and you are accepting that. These are the two errors, type 1 and type 2 error. So probability of committing type 1 error, we have to minimize that. Okay, this is like a core trial system, that we must minimize type 1 error. Okay, so we try to minimize type 1 error, which is known as level of significance. So we start from the 1%, 5%, 10%, maximum 10%. Okay. Now, degree of freedom is very important in case of regression analysis. In case of simple mean analysis, it is n-1. We know that. In case of regression analysis, it is n-k, degree of freedom, number of observations that are free to vary. So n-k, n is number of observations, sample size, and k is number of parameters to be estimated. So in case of simple regression function, we have two parameters, beta 1 and beta 2. So it is n-2. Okay. Now, next stage in hypothesis testing is to find t values. You can find t values on the same lines as in case of mean testing. Mean analysis जो आप करते हैं statistics में, beta 1 cap estimated value minus beta 1 true value hypothesized value divided by standard error of beta 1. This is t value which follows t distribution with n-3 degree of freedom for multiple regression model, for 3 variable regression model. Okay. Now, mostly we test two types of hypothesis. One is significance of individual coefficients, and next is significance of all the coefficients jointly. So we test whether beta 2 is significant, whether beta 3 is significant. Okay, so this is testing of individual coefficient, and then we go for joint testing, whether beta 2 and beta 3 both are equal to 0 or not. So that is joint hypothesis testing. First is individual significance. So for testing individual significance, null hypothesis is obviously beta 2 is equal to 0. That beta 2 does not matter. It has no effect. X has no effect on Y. Okay, beta 2 is equal to 0. And alternate hypothesis is two-sided, and it is beta 2 does not equal to 0. Okay, the meaning is that X has no effect on Y. We are simping a very plain hypothesis. Okay. Now the steps involved are first calculate t value. Again, this is same estimated beta 1 or beta 2 cap and divided by standard error of beta, because in hypothesis the value of beta is equal to 0. So simply beta 1 cap divided by standard error beta 1 cap. Okay. So find this calculated value. Then next decide about the level of significance, whether you are comfortable with 1% or 5% or up to maximum 10%. We cannot move more than 10%. Okay. So once you have decided level of significance, find tabulated value by level of significance and degree of freedom. If you are suppose you are looking at the t table, there is a need of level of significance and degree of freedom for tabulated value. So find tabulated value. Now next is, if your calculated value in the first step is more than tabulated value, okay, you may reject the null hypothesis, and rejection means that beta 2 does not equal to 0, and the meaning is that X has a significant effect on Y. Okay. Now there is one rule of thumb. If t value, if your number of observations are more than 20, in most of the cases number of observations are more than 20. Okay, so if your number of observations are more than 20 and your t value of any particular calculated t value of any particular coefficient is more than 2, in most of the cases we may reject the null hypothesis. There is no need to look at any table. There is no need to decide about the level of significance. Okay, just look at the t value. If it is more than 2, you can reject the null hypothesis. Okay. Now next is overall significance, joint significance. Null hypothesis is beta 2 is equal to beta 3 is equal to 0. Okay, jointly they are equal to 0. For that, for joint significance, we need F test. Okay, now F test, the formula of F test is explained sum of square divided by degree of freedom divided by residual sum of square divided by degree of freedom. You know what is explained sum of square, you know what is total sum of square. Residual sum of square is that portion of Y which is unexplained by excess, all the X. Okay, so it is residual sum of square. F value, calculated F value is basically ratio of ESS and its degree of freedom divided by RSS and its degree of freedom. Okay. Now this calculated value follows F distribution with 2 and n minus 3 degree of freedom. Okay. In case of multiple regression framework, it follows 2 and n minus k degree of freedom when you have k variables. Okay. Okay, last, once you have done all these things, hypothesis, everything, you can also use some model selection criteria for selecting a best model. Okay, so there are a number of criteria that are reported by software automatically. Okay, you can use AIC, SPC, or any criteria. They are basically adjustment to the residual sum of a square for addition of additional variable in the model. Same on the line of adjusted R square. In case of adjusted R square, there is an adjustment for addition of explanatory variable. Here also there is addition. There is an adjustment for addition of explanatory variables. Okay. So thank you for today's lecture. This is all that I have. Now the floor is open. If you have questions, I think we have some time. So you must ask. You must feel free to ask. Okay. I would like to respond all the things.
Yes, it is open. I have allowed the participants to unmute yourself. If you have any doubt, then you can ask us.
Good afternoon, sir. This is Umar Wasil from Baramulla, Kashmir. Sir, I have a question. Sir, if correlation and regression both measure the relationship between the dependent and independent variable, so what's the need to go for the regression analysis if there is also correlation available as a simple model?
Okay, fine. You have a very good question. I missed it. When we use correlation analysis or correlation coefficient, okay, correlation coefficient simply shows the degree of linear relationship between two variables. If the value of correlation coefficient is suppose 0.90, we can say that there is a high correlation between y and x. Okay. Now, we are not sure about the direction of relationship in correlation, whether x is causing y or y is causing x. It is not clear in that magnitude. We can say it is high with the 90% value, but we are not sure about that. Okay, we are not sure about the exact magnitude of relationship that we get in the regression analysis. In case of regression analysis, we assume that there is one cause variable, there is one effect variable, and ultimately you get beta 2, that beta 1 and beta 2, and those value tells us the exact magnitude that once we change x by 1 unit, there will be that much change in y unit. So these things are not there in linear in simple correlation analysis. Okay.
Okay, sir. Sir, another question I have. Sir, as you were talk about this level of significance. So, sir, is there any criteria to select the level of significance, or it's up to the researcher? It's up to the
researcher. You must choose a minimum value. Start from 1%. Okay. Then, if you are not able to reject at 1%, you can move towards higher level of significance. Now, the problem of table is that you have to jump from 1 to 5%, then to 10%, because tabulated value are given at those. Now, software report p values. Now, p values are basically they are exact level of significance. So, suppose the reported p value is 3%. Okay, so that means it is an exact level 3% at which you may reject the null hypothesis. So due to reporting of p value, there is no need of choosing level of significance, because software give you the exact level of significance which are there in the form of p values. Okay, so you can choose p values. You can take your decision on the basis of p values. Okay.
Thank you, sir. Thanks a lot.
Vartika, do you have a question?
Yes, sir, I have two questions.
Okay.
First question is that if in a regression analysis, I have many variables, many independent variables, how do I make a selection of which, say, for example, I have 15 variables and I want to only take, say, 4 or 5 variables. So how do I choose those variables? And second, sir, I want to ask is that if my variable is a qualitative variable and I cannot put it in an ordinal scale, say, for example, social category, I can't put it in, say, ordinal scale. So how do I use regression for that particular variable?
Okay. Now, for your first question, as far as selection of variables is concerned, okay, first you have to use theory. There are theories, there are past work. So on the basis of all, after reviewing all the past literature and theory, ultimately we decide few variables. Okay, then suppose you have a lot of variable. Okay, so next is it is guided by the availability of data. If you have limited set of observations, suppose your sample size is very small, then it is preferable that you must drop some variable. You cannot involve, you cannot include number of variable because you will lose degree of freedom. Okay, so on that stage you can trim your model. You can drop some variables on the basis of successively on the basis of hypothesis testing. Okay, so these are the things that we use. We use theory, we use our own observations, we use statistical significance. Okay, and if data allows, you can add number of variables if your sample size is quite large. Okay, so in that case it is better to build a model which include everything that matters for the model, okay, but does not include any irrelevant variable. Okay, so this is one thing for as far as your first question is concerned. Now, as far as second question is concerned, that how we can include ordinal or nominal variables or any variable. Now, in regression analysis, you can include everything. There is a part in econometrics which deals with such variables, or purely qualitative variables. Okay, so in a statistical framework, you can do ANOVA analysis and COVA analysis. Okay, but I will suggest that you must also do all those things within the framework of regression, because there are additional benefits of doing that. Okay, so the problem is when your dependent variable is qualitative. If your dependent variable is qualitative, then you have to resort to some very difficult methods, okay, which are limited dependent variable models. If your independent variable is qualitative, okay, it is not problematic. Most of the things are very simple, okay, and even the interpretation is simple. So that is on the line of simple regression framework. So hopefully I will try to cover in the next class.
Thank you, sir. Thank you.
Okay, any other?
Madam? Yes.
Yes,
Are
good
you hearing me?
afternoon, sir.
Yeah, I can hear.
Yeah. Okay. Just
We'll have Sakshi first. Sakshi, ask your question. Vertical,
okay. Yeah. Okay, I have one question, sir.
Yeah.
Okay, I'm looking from Ethiopia.
Hmm.
Okay, can error term become 0, or is there a situation at which an error term become a 0? Because error terms is the difference between the actual and the sample difference. So is there the probability to get the error term 0? This is my question. If we face such type of situation, how could we solve it? And just thank you for your nice presentation. And if you add your presentation for future, maybe our own dependent variables, 2 dependent variables such as structural recursion modeling, which is new model, not only on regression. So it is better for us if we say something on it.
Okay. Now, as far as your question is concerned, now the value of u. So when we say particular u, so they are not 0. There are some u's which are positive. There are some u's which are negative. But the average value of u okay, is by assumption it is 0. We are assuming that the average value of u is 0, okay, and for in case of sample, okay, when we deal with the sample regression function, it is 0 by the mechanics, the method which we use, okay, it is 0 by that, because we are trying to minimize the sum of squared residual, okay. So by that mechanism, the sum of residuals is 0. In case of population, it is 0 by assumption. We are assuming that the sum is 0, okay. So the sum is 0, but individual values are, it is all the values are 0 only when x, there is an exact relationship between x and y. So if there is an exact relationship, x is explaining everything, every variation of y, all the variation of y, and there is nothing like u. All the u values are 0. So in that particular case, when there is an exact relationship between x and u, individual values of u may be 0. Okay.
Good afternoon, sir. Am I audible?
Yeah.
Good afternoon, sir. Good afternoon, ma'am. First of all, thank you very much, sir, for such an informative workshop, and you have covered most of the points. My question is regarding 2T rule of thumb. Okay, where suppose we are testing the hypothesis, and if the errors are about 20, we are supposed to reject that hypothesis. Then in that situation, suppose I'm testing the hypothesis and I realize this particular rule has come. Then what I'm supposed to do, sir, then? Am I supposed to form another hypothesis?
2T rule of thumb is that if you have sufficient number of observations, more than 20, okay, and your T value is more than 2, okay, so you may reject the null hypothesis. Okay, rejection means when you are rejecting the null hypothesis, that means your coefficient is significant. Okay, it is not equal to, rejection means it is not equal to 0, and that particular value is significant, that particular x is significant. Okay, it has significant effect on y. So I think there is no confusion in that.
Okay, thank you, sir. Thank you very much.
Thank you.
Okay, quickly, Sakshi, ask your question, and then we'll end the session.
Yeah.
Sakshi, do you have a question? You have raised your hand.
No, ma'am.
Lower your. I think that's all the questions have. And with this, we come to the end of our today's session. And on behalf of Department of Economics, I would like to take this opportunity to place on record our hearty thanks to Dr. Tariq Masood, sir, for the perfect explanation of regression analysis. I think no one could have done it better the way you have done it. I was totally, I mean, even I was listening and understanding a few concepts that were not clear on my end. I must appreciate that Dr. Tariq Masood has described the concepts of simple and multiple regression analysis along with the fundamentals of regression models and in-depth explanation of various models along with their equation. That is, each and every point, each and every equation was explained really well. He has tried his best to explain the concepts with very basic description, and I think it was comprehensible by all the participants. And the way you have explained statistical inference and the various steps to test the hypothesis, it was very explanatory for all of us, I believe. Thank you so much, Tariq sir, for giving us time today.
Thank you, ma'am. Thank you, ma'am, for invitation. I think there are some issues that we will discuss in the next class. Okay. So,
also, we have Tariq sir. So I think all of the participants would be eagerly waiting to attend tomorrow's session as well.
Ma'am, PPT, share a PPT for us, ma'am.
I will share PPT. Okay. But basically, I will tell in the next class that they are from a particular book. Okay, I try to write them from a particular book, so you can follow all those books. Okay?
Sir, I have a request to you.
Yeah.
Sir, tomorrow is also your this session.
Yeah.
Sir, on time series analysis.
Yeah.
So, sir, is it feasible for you to give some tips on paper writing tomorrow?
Paper writing
Because,
is different. I think that there may be some other person for paper writing, but I will try to explain. I will try to explain how to write empirical paper. Okay? Issues involved in the writing of empirical paper. Okay,
okay, sir. Thank you.
On your request. Okay, so tomorrow, I think Friday, we can start at around 2:10 or if it is.
2:15, if you say.
We can start 10 minutes late.
Yes, sure.
Okay.
Okay.
Thank you. So can I leave?
Then yes, we conclude, and thank you so much, sir. Thank you for joining us today.